evening. Yeah, welcome everybody according to whatever time zone you're in. Welcome to day 2 of the workshop. First off, we're happy to have Hayden Lee of Harvard. Hayden is joining us from New Zealand, so this is at midnight his time. So we're very, very happy to have you talk, Hayden. Thank you.
Okay, thank you, Paul. Hi everyone. First, I would like to thank Enrico and Guy for putting together this wonderful online workshop, and it's a great pleasure to be able to present this talk. So over the past several years, there have been a growing number of activities in trying to understand the structure of cosmological correlators from a number of different perspectives, and we've seen some highlights of those activities from the talk so far. In my today's talk, I'm excited to tell you about the recent progress on our work on the bootstrap approach to cosmological correlators extended to spinning particles. So my talk will be based on the series of 3 papers written in collaboration with Nima, Daniel, Guy, Carlos, and Austin, especially the latest one. So Carlos and Austin already gave very nice talks on highlighting some of our results, and general bootstrap philosophy was beautifully outlined in Enrico's talk yesterday. Also, I saw that there were lots of interesting discussion regarding the general cosmological bootstrap program in yesterday's discussion session. I'll probably reiterate some of the things that were already discussed before, so please bear with me on that. But hopefully I'll also entertain you with some interesting new stuff as well. So let me begin. So I know that this particular audience probably doesn't need a long introduction to cosmological correlators, but just so that we are on the same page, let me briefly talk about the motivation of our work before going into details. So in cosmology, we are ultimately interested in understanding the origin of larger structure of the universe. Although we don't quite have direct access to the past history of the universe itself, fortunately, there are statistically enough number of structures in our observable universe, which allows us to measure spatial correlations between cosmological structures at late times. The central challenge in cosmology is then to reconstruct a consistent history of the early universe that explains the origin of these correlations. A key fact that we have discovered from the measurements of various 2-point correlations in the late universe is that all cosmological structures seem to have been correlated in an apparently acausal and a nearly scale invariant way. So the question that we would like to ultimately understand is what early cosmic history gave rise to primordial fluctuations that seeded these seemingly special correlations at late times. A particularly elegant early universe scenario is offered by inflation, in which primordial fluctuation arose from vacuum fluctuations that got amplified due to the exponential inflationary expansion and set up initial conditions for later structure formation. In this picture, local physics, such as particle creation and decay, occur during inflation's far past, and fluctuations evolve in time and get imprinted on correlation functions that live on the future boundary of an approximate de Sitter spacetime. These boundary correlators in an approximate de Sitter are what encode the physics of inflation and therefore form a central set of objects that we would like to study and compute in cosmology. The textbook method for computing these correlators is by writing down Lagrangian and computing Feynman diagrams. This method naturally tracks local time evolution of particles in the bulk at every step in the calculation, but the price of making this locality manifest is that this Lagrangian formalism inherently involves a lot of redundancies, involving gauge transformations and field redefinitions, which in many cases make the computation rather complicated. And moreover, there can be some practical difficulties associated with evaluating time integrals. That is an intrinsic part of the calculation of these correlators in the Lagrangian framework. On the other hand, after we are done with the calculations, we often find that the final answers for these correlators are surprisingly simple. And probably a good illustration of this would be Malta-Senner's calculation of the throughput function, which is a rather complicated calculation if done in the ADM formalism. So this kind of observation of simplicity in the final observables is actually not very new, but rather it has been a recurring trend in high energy physics. Instead of thinking of Lagrangian and Feynman diagrams, the bootstrap philosophy, which is to focus directly on the observables using only physical degrees of freedom, has proven extremely useful, and for example, has led to an especially huge progress in the modern studies of scattering amplitudes. So all of these also very much motivates us to try to get rid of the intermediate story of bulk time evolution for our cosmological problem, and try to see if we can simply write down or bootstrap the answer for these boundary correlators. over the past several years, a number of studies have been undertaken to understand the structure of these correlators using more boundary-centric frameworks. So the types of foundational questions we hope to understand better from this boundary perspective include what are the fundamental rules that govern the structure of cosmological correlators, and how these rules are encoded in the analytic properties of these correlators. So currently, we do not fully understand what the complete set of these rules are, but as people already pointed out, we think that the boundary framework, which doesn't rely on a model-wide model analysis, is more naturally suited to addressing these type of questions about the general consequence of physical principles. So one thing we expect from these correlators, though, is that they should arise from local time evolution in the bulk, beginning from the far past, where the space-time looks effectively flat. This means that notions such as Lorentz invariance and unitarity that captures the essential physics of scattering amplitudes deep in the past should somehow be encoded and emerge from the structure of these boundary correlators. And indeed, as I will describe in a bit, and already been discussed in many other talks, scattering amplitudes are actually contained inside a kinematic subspace of correlation functions in a rather remarkable way. So we'd like to see if any of the deep physical and mathematical structures that have been discovered for amplitudes have any counterparts for.
Sorry, Hayden. Sorry to interrupt. There is some issue with echo. So I will ask everyone that is on Sokoko or talking on Sokoko to switch off your mic. I don't understand why, but some people are getting echo from your talk.
Yeah, I just turned off, closed the page on Sokoko, and it stopped.
Okay.
Or muting it
so
also.
I think there is, yeah, so now it's fine. There was Yasha that had his microphone on Sokoko on, and that was creating the echo.
Ah, I see. Okay. So now.
Yeah, so now he turned it off and the echo is gone, so you can go back to Sokoko.
Yeah, apologies, Hayden. Maybe you can backtrack a minute and then carry on.
Is it okay now? Is it working well?
For me,
Okay.
yes.
For me, yes.
Yes.
Okay, then I shall continue. So yeah, so one can probably mention lots of other theoretical motivation as well. But the study of cosmological correlators also has some high practical relevance. So on a much more practical level, we just want to learn the rules for efficiently calculating non-Gaussian correlators that will be useful for comparing with observations. And we hope that with the new theoretical tools developed in this approach, would also allow us to have a large extension of the cosmological collider physics program and non-Gaussian phenomenology to incorporate more realistic and observationally relevant scenarios. Okay, so with that motivation, I will try to advocate a bootstrap approach to cosmological correlators for the rest of my talk. As with the study of amplitudes, the key idea of this approach is to exploit symmetries and singularities of the observables to directly determine them without Feynman diagram calculations. While we are still far from knowing all the rules, we have by now understood several important physical singularities that seem to control the analytic properties of cosmological correlators. Because these will appear many times in our discussion, let me try to spend some time here to give a preview of what these singularities are, and we will later see how the knowledge of these singularities can be used to uniquely reconstruct correlation functions. Okay, so there are basically 4 types of singularities we will make use of. Probably the one that are most familiar to many of you is the so-called total energy singularity, which is reached when the sum over all external energies or the magnitudes of spatial momenta goes to 0. Because all physical energies are necessarily positive, we can only reach this singularity after analytic continuation of the energy variables. And indeed, we'll find complex analysis extremely useful for this business of studying correlation functions. This singularity also has a particularly nice physical interpretation. Namely, at this singularity, the total energy goes to 0, which means that we are effectively restoring energy conservation in flat space. And for this reason, the coefficient of this singularity is precisely is given by the scattering amplitude in flat space. And as we'll see, this provides a very strong constraint on the allowed form of correlation functions. And a closely related cousin is the so-called partial energy singularity, reached when the sum of our energies in a subgraph goes to 0. This enforces energy conservation at one of the vertices appearing in a graph, which results for the correlator to factorize into a product of a lower point amplitude on the side where the energy is conserved and a low point correlator on the other side. Actually, strictly speaking, the low point correlator is given by the so-called shifted wave function, but I'll try to give its precise definition later in the talk. So this limit is very similar to the factorization limit of amplitudes when an intermediate particle goes on shell. And later on, we'll make an extensive use of this property to compute correlation functions. So these two energy singularities exist off the physical region, since both of them require taking some of the energies to be negative. But there are also potential singularities that could exist for physical momentum configurations. So let's look at those. And so in this other space, correlation functions can potentially have a singularity in the so-called folded or collinear limit when two of the external momenta become collinear or parallel to each other. And it is well known that this limit is a proof of initial state. And if we start from the Bunch-Davies initial vacuum, the singularity should actually be absent, so that the correlator should be regular in this limit. And lastly, the correlator should be free of any bad singularities in the soft limit when an external energy is taken to be 0. So by bad singularities, I mean anything that blows up apart from those coming from some normalization factors. Okay. So together with conformal symmetries, which are obeyed by the de Sitter correlators that we'll study, these singularities provide crucial physical inputs in determining the structure of correlation functions without bulk calculations. And we'll see a number of examples later in the talk. Okay, so the outline for the rest of the talk is following. So first, I will review the structure of scalar correlation functions in the De Sitter space. Next, I will describe basic properties of spinning correlation functions. And then I will describe some consistency criteria for correlators that are similar to the full particle test for amplitudes in flat space, and show how these constraints can be used to basically reconstruct spinning correlation functions. And finally, I will end with some outlook.
Sorry, Hayden, before you move on, can I ask you a question about the collapse limit singularity? So I know that in perturbation theory or in specific examples that like people have particle production during inflation, they know that you have this sort of collinear singularity, but is there any, do you know any work that this has been like proven non-perturbatively, that Bunch-Davies vacuum necessarily leads to the lack of such singularity? Or it is just by, it is in hindsight that it is known?
I guess, first of all, you're talking about the collinear singularity, not the...
No, sorry, yes, collinear singularity, yes.
Yeah, I think it's actually easy to see this from a bulk perspective by, because in order to have this kind of folded singularity or collinear
No, I know that in perturbation theory by explicit manipulation, you can show that it doesn't exist. But I was wondering, I mean, if there is a more general argument about that, non-perturbative argument, perhaps.
Yeah, I think. Yeah,
sorry,
at this stage,
we have to discuss it later, but.
Yeah, we can also discuss it later. But I think at this stage we are always going to work in the perturbative setting. So I think also another way to see this probably is by going to the flat space limit by going to the total energy singularity. So in that limit, we know that everything should be reduced to the flat space amplitude. And in that case, the residue at the total energy singularity needs to be precisely Lorentz invariant. And that's only possible if you start from the Bunch-Davies initial vacuum that has the same mode function as the plane wave solution as in flat space limit. So I think that could be one interpretation of this in the perturbative framework. But yeah, I also agree that yeah, non-perturbatively, I don't know any proof of this.
Thanks.
So we can also talk about it later.
I just wanted to mention that the amplitude doesn't have to be Lorentz invariant. You could have interaction for which the amplitude breaks boost. And then I think this result is still true that you don't have such singularities. So hopefully there is an explanation that does not rely on Lorentz invariance for the absence of nodes. Because I think it's true.
That's very interesting point. Yeah. Okay. All right. So let's move on. So to begin, let's first look at the symmetries of these little correlators. First focusing on the 4-point function. So in addition to the usual spatial isometries, boundary correlation functions in this sitter have extra symmetries, which are derivations and special conformal transformations. So these symmetries give rise to this particular set of differential equations for the de Sitter 4-point function, which is denoted by this symbol F. It turns out that the action of the conformal group becomes simplest for conformally coupled scalars. So let's first try to analyze the 4-point function for this special case. So first, the derivative constraint is nothing but the condition that F needs to have a scaling dimension of -1. And to solve this constraint, we can simply pull out a vector of the intermediate momentum S, as indicated in this picture below, which turns out to be a convenient choice. And the rest of the functional dependence, which is denoted by F hat here, is then characterized by just 2 dimensionless variables, which can be also chosen to be the ratio of S and the sum over 2 momenta on each side of the 4-point function, which we denote by the variables U and V. The special conformal constraint is in general quite complicated to solve, but it takes this nice reduced form for the special case of conformal scalars, given in terms of this hypergeometric operator. So our task is then to basically classify the solution to this conformal invariance equation according to their singularity structures that correspond to certain physical processes in the bulk. Of course, the previous equation is completely non-perturbative, as it's just a kinematic requirement, but we will be interested in obtaining solutions order by order in perturbation theory, starting from the simplest analytic structure. So let's try to see what the structures are for this 4-point function that arise from tree-level processes in the bulk. So first, contact diagrams have the simplest possible analytic structure and are only controlled by the total energy singularity, which must be present in order to guarantee the correct flat space limit and reduce to the contact amplitude in flat space. So the simplest candidate function that we can write down is simply 1 over the total energy, 1 over E. And quite nicely, it can be checked that this function indeed satisfies the conformal constraint and be matched with the 4-point function arising from the phi to the 4th interaction in the bulk. And with the knowledge of this simplest solution, it then becomes trivial to build higher order solutions, which we can do by simply iteratively acting with this delta U operator on the lower order solution. Because delta U operator basically commutes with both delta U and delta V appearing in the conformal constraint equation. So we can simply pull out this delta U factor. And it turns out that these solutions are in 1-to-1 correspondence with contact interactions in the bulk, with the order of the total energy pole matching the number of derivatives of the contact interaction. So this boundary formalism.
Sorry, why do you say 1-to-1 as opposed to many-to-1?
Right, so yeah, in general, yeah, it will be some linear combination of contact interactions in the bulk. Yeah, that will contribute to one particular contact term written in this basis. So,
but would you expect it to be rather many-to-1 in the sense that there is a degeneracy of operators all leading to the same correlator or not? The motive would be if you consider a field redefinition that dies at the boundary, you would expect 2 operators that differ by such a field redefinition to have the same correlators. And so I would have maybe naively expected a many-to-1 going from the many operators to the correlator, but I haven't studied it in this case specifically.
Yeah, because the Lagrangian language, yeah, you can always make field redefinitions. So the contact interaction you're talking about is not a unique, may not be a unique choice. I think what I want to say is that the order of the pole in this contact diagram is controlled by the highest number of derivatives in the interaction. So there is a 1-to-1 matching with those, but yeah, it may not be exactly 1-to-1 in the sense of one interaction corresponds to a particular contact diagram in these spaces.
Can I ask one question? I mean, you say when you say one-to-one, usually the contact terms are classified by S to the power n, T to the power m, two Mandelstam invariant. Here instead, you only have delta U to the power n. So in which sense is one-to-one? There are some other contact terms that should not be expressible in this way.
Yeah, thanks for pointing out, Massimo. Yeah, actually, this is true that this particular basis of contagrams only covers Mandelstam S to some power in flat space limit. So in order to also compute, also include these other contact terms, you have to look at some other structures.
And so is there a rule that you have got them all, or how do you know?
Yeah, so usually these kind of contact terms arise when you integrate out intermediate spinning particle. Whereas here, this type of contact term only arises when you integrate scalar intermediate particle. So this contact terms these contact terms that arise when you integrate out just a scalar particle does not form a complete basis of all the possible contact diagrams. So in those cases, you can also write down, you can basically solve for the 4-point function with spinning exchange. And then you can also look at the contact diagram contribution to that particular 4-point function. And those would give you these missing contact terms.
And do you have such a result has already been derived, or it's
in our original paper, we also derive, so basically you can look at our solution for the general spin exchange, and so basically you can derive those by acting with certain differential operator on this seed function. So this particular scalar contact diagram will provide a seed for all the other possible contact terms, and you simply have to act with a certain derivative operators that basically raises the spin correspond to the exchange diagram, and you will generate the other contact terms in that way.
Okay, thanks.
Do you have a proof that you can get all of them? You can get some of them for sure, but do you know whether you can get all of them?
Yeah, I think you can take the flat space limit and then match with the contact interactions in flat space and see that you can reproduce all the context structures.
How do we know there's nothing that map doesn't have a kernel? Do we know that?
Well, we do know that it has a kernel because the field redefinition gives you no total energy pose. So
okay, so
so there is a kernel, but which is made by boundary terms and field redefinitions.
So maybe it's still an open problem, maybe.
Yeah, I think that this issue that Enrico is pointing out, we haven't fully classified things without the TOTO singularity. So they could be additional contact-like interactions.
Okay.
Okay. So basically this gives all the contact terms that arise from integrating out the scalar intermediate particle. So the correlator with the next simplest analytic structure we can consider is the tree exchange correlation function with the scalar exchange. So in addition to the total energy singularity, the tree exchange diagram also are controlled by the partial energy singularities that I mentioned before. So the presence of these singularities can be easily seen from the equations that the exchange diagram satisfy, which are this pair of ordinary differential equations in UV. So these equations can be derived in a number of ways, but a quick way to see that they make sense is to take the large mass limit by sending mu to infinity, where mu here is roughly the mass of the intermediate particle in Hubble units. So taking this limit is equivalent to integrating out the intermediate mass particle, scalar in this case, in which case the 4-point function should be described by the contact diagram in the low energy EFT, and this is what precisely this limit gives us. So the task of obtaining the exchange 4-point function then boils down to solving one of these second-order ODEs. And because it's a second order equation that we are solving, to fix the solution, we need to impose two boundary conditions. So we can impose these conditions by demanding a specific behavior of the solution in special kinematic limits. So one of the limits we can take is the collinear limit that I talked about. So the most general solution has a singularity in this set, but when we require this to arise from the Bunch-Davis initial condition, this singularity should be absent. So that's one boundary condition that we can impose. Another special kinematic limit we can look at is the so-called collapse limit, in which the intermediate momentum is taken to 0. So this is the limit in which there's a large separation between the two decays of the intermediate massive particle. So very similar to the factorization of scattering amplitudes, the intermediate particle goes on shell and become long-lived and become factorized. So, so the solution in this limit should also behave as a product of two 3-point functions. So these are the two independent boundary conditions that we can impose to uniquely fix the solution to the differential equation. So for simplicity, let me just show you the solution in the small u limit. So the general solution. Yeah.
So since you're solving conformal Ward-Takahashi identities for 4-point functions, so the general solution should involve a function, a general function of cross ratios. So it's not just boundary conditions. You also have a whole function worth of data and a function of two variables. So how has this been fixed in this procedure?
Yeah, so this is the boundary condition that you impose to specifically solve this equation that tree-level diagram satisfies, which is the bottom equation.
But that's, it was still equivalent, as you showed us earlier. This was just coming from the conformal Ward-Takahashi identities.
Yeah,
so
it's not equivalent to. So we are demanding that the tree-level exchange diagram satisfy both the conformal invariant equation as well as this tree-level diagram equation. So this tree-level equation needs to be satisfied as well as the conformal invariant equation. So not the same equations.
I see. So you impose an additional condition that this is tree-level.
Yeah, exactly. So we are restricting our solution to so that it additionally satisfies this particular ordinary differential equation on top of the conformal constraint.
Okay.
Yeah, so it's the boundary condition to this particular ordinary differential equation that that I'm talking about. Okay, so yeah, so if you look at this solution in the small u limit, we see that the solution consists of two parts. So the first part is the particular solution to the inhomogeneous differential equation, which we see as an analytic function that can be Taylor expanded around u equals 0. And also we see that each term in the series is power law suppressed in the mass parameter for large masses. So this part of the solution describes the EFT expansion in the bulk when you integrate out the intermediate particle. The second term is perhaps physically more interesting. It is the homogeneous solution that we were forced to add by the boundary conditions, and it is a non-analytic function that oscillates around u equals 0. And this oscillatory behavior is a fingerprint of the time evolution of massive particles in the bulk, which I think nicely shows up as a purely boundary way as a solution to the conformal invariance equation, together with consistency requirement. Okay, so also knowing the full solution makes it possible to analytically continue and to the complex plane and allow us to see all the energy singularities. So here on the left figure shows the tree exchange 4-point function in the complex U plane, where the physical momenta here belong to the interval between 0 and 1 on the positive real axis. We see that the solution has a branch cut running along the negative real axis between -1 and 0. And this is precisely coming from the homogeneous oscillating solutions that correspond to particle production. And it turns out that the discontinuity of the solution at the location of the total energy singularity, which is reached when you send u to -v, is precisely fixed given by the Wronskian of the two homogeneous solutions that are just coming from the particle production piece, which can then be recognized as the 2-to-2 scattering amplitudes in flat space. So I think this kind of provides a nice illustration of the link between scattering in flat space and particle production in curved space. And the right panel here shows the behavior of the solution within the physical interval between 0 and 1. And we see this oscillatory behavior in the limit as u goes to 0, which corresponds to the limit where the 4-point function becomes collapsed and the intermediate momentum goes to 0. And we see that the frequency of these oscillations is precisely fixed by the mass of the particle. So these oscillations provide a rather interesting signal that we can look for in observations and try to constrain the particle spectrum during inflation. Okay, so that was a kind of quick review of the structure of scalar 4-point function in de Sitter. So let me now move on and describe the properties of de Sitter correlators for external spinning operators.
Sorry, one question.
So, yeah.
Very brief. I mean, there is this connection between particle creation and flat space because you're looking at a conformally coupled field that lives in flat space. So it's not really particle creation in curved space-time because the field is conformally coupled. Or am I saying that?
This kind of analytic structure also holds for any scalar particle. So you can also, starting from this 4-point function of conformally coupled scalars, you can also obtain the 4-point function of massless scalars, which are not conformal. And you will see exactly the same cut structure for that object. So you can also take the discontinuity of that solution for massless scalar function, and you will exactly find the same link between.
Yeah. So that would be maybe more close to the particle production in actually curved space-time.
No, but this is particle production curved space-time because it's the non-perturbative, like it's a Schwinger like effects that one is seeing from these oscillations. There's a e to the minus m over h appearing in front of the particle production parts. The exchange particle does care about the fact that you're in de Sitter, even if the external particles are conformally coupled.
Oh, now I understand. Because the exchange one knows where you are, and so okay, now I understand.
Yeah.
Okay. So one reason we might want to understand spinning correlation functions in de Sitter is because the graviton is amongst the two massless fields that play a particularly important role in cosmology, because their fluctuations get amplified during inflation and survive until late times, so that correlation functions of gravitons are potentially observable. In flat space, we have learned that the amplitudes for massless spinning particles are remarkably simple, and take the following concise expressions for spins 1 and 2. And this is essentially because massless spinning particles are mediators of long-range forces, which are highly constrained by locality and unitarity. And of course, the discovery of this simplicity for gluon amplitudes is what motivated the modern amplitudes bootstrap. To date, however, not much is understood about massless spinning correlation functions in de Sitter beyond 3-point functions due to the algebraic complexity of calculating them. So we are motivated to see if the bootstrap approach can help us to compute them and see a similar simplicity for spinning correlation functions. So to study spinning correlation functions, it's actually quite useful to consider the wave function of the universe defined at the future spatial size of de Sitter, which, for example, take this form for a bulk field, a scalar field phi in momentum space. Since all boundary conditions, boundary correlation functions can be restored with the knowledge of the wave function by the usual rules of quantum mechanics, and it's actually trivial to do so in the perturbative setting that we are working in, the wave function provides a more basic object that captures cosmological fluctuations. And the reason why it's often useful to consider the wave function instead of bulk correlation functions directly is that the wave function coefficients, denoted by psi n here, little psi n here, are a particularly nice object to study, which can be interpreted as correlation functions of operators dual to bulk field in a CFT. So for example, a massless spin 1 field in the bulk is dual to a conserved current on the boundary, while the massless spin 2 graviton is dual to a stress tensor. So studying this object is useful since they obey the same kinematic constraints as correlation functions in the CFT. And for this reason, for the rest of my talk, I will use a slightly abused terminology and simply refer to wave function coefficients as correlation functions. But it should be understood that they can be translated to correlators to bulk fields in a straightforward way. Okay, so we are interested in computing correlation functions involving conserved currents on the boundary. They are, however, conserved only up to contact terms, that is, up to terms that are proportional to delta functions in position space. This conservation requirement as separated points then leads to this Ward-Takahashi identity for these correlation functions, which in momentum space take these expressions for spins 1 and 2. So what this identity tells us is that when you take the longitudinal part of or the divergence of the correlation function, that should be fixed in terms of some linear combination of lower point structures. In general, solving this Ward-Takahashi identity in momentum space is quite challenging. This is because contact terms now become non-zero in momentum space and have an effect of shifting this momenta on the right-hand side of this Ward identity. So it really turns into an inhomogeneous equation for spinning correlations. Also, the added challenge is that we also need to impose conformal symmetry of the correlator, which is quite complicated to do for spinning correlation functions. So for this purpose, it turns out to be quite convenient to introduce spinor helicity formalism adopted to cosmology, and then consider the spatial conformal generator in terms of these spinor helicity variables, which take this particular form on the left bottom. So nice advantage of considering this spinor representation of the conformal generator is that when it acts on the purely transverse components of the spinning operator, which is done by contracting all of its indices with polarization vectors, it first of all, it reproduces the ordinary conformal generator, but that actually should be zero inside a correlation function. But it also spits out the divergence of the operator. So this means that we can simply keep track of the transverse part of the correlator and still be able to check the Ward-Takahashi identity. So it turns out to be a huge advantage to do so, since the longitudinal part of the correlator is typically very complicated beyond 3-point functions. So as a result, by combining the Ward-Takahashi identity with the spatial conformal generator, we arrive at the following single equation that imposes both conformal symmetry and current conservation simultaneously. So this equation takes the form of an inhomogeneous second-order differential equation, and its solution can be schematically represented in the following way as a sum over the particular and the homogeneous solutions. So from the bulk perspective, the particular solution corresponds to the correlator that arises from minimal bulk coupling, whereas the homogeneous solution is general unconstrained and corresponds to correlators that arise from non-minimal couplings or higher derivative operators. So the homogeneous solution is the one that gets annihilated by the action of the spatial conformal generator. So to obtain it, so we simply have to with certain transverse traces projector on a structure that has the right quantum numbers. So it turns out that they're relatively easy to obtain. On the other hand, it is in general quite difficult to find a particular solution to the Ward-Takahashi identity, since there are still lots of tensor structures to keep track of. And it is possible to solve this. Well, it is possible to solve this in a direct way for 3-point functions, which were, for example, done in these references by Maldacena, Pimentel, Bzowski, McFadden, Skandaris. But we will need better strategies to solve this equation for 4-point functions and beyond. Okay, so in our paper, we have used 2 complementary approaches to construct spinning correlators on the boundary DS. In the first method, we used the so-called wave-shifting operators to generate spinning correlation functions. So these wave-shifting operators are certain differential operators that map solutions of the kinematic conformal constraints with different quantum numbers. This means that we don't have to resolve or solve complicated conformal constraint equations for tensorial correlators, but rather we can build solutions by acting with certain differential operators on the scalar solution that we have found. So these operators are easily constructible in embedding space and have been extensively studied in the conformal bootstrap literature. And in our work, we have constructed the Fourier space version of these operators for our cosmological applications. So the strategy is then to generate a general conformal structure as a linear combination of various tensor structures that have the right quantum numbers. The coefficients are then fixed by plugging this general correlator back to the Ward-Takahashi identity, and then by matching with the low point structures. It turns out that this procedure is very algorithmic, as you can imagine, but it turns out that it can be still computation intensive, since we still have to keep track of these multiple tensor structures in the intermediate process. But in any case, this can be done for
Can I ask a question here? Do you know whether this procedure can generate the general case? Do you have a complete basis, or you have some solutions?
Yeah, so if you have spinning correlation function, in general, you always gonna have some multiple tensor structures allowed by conformal symmetry. So you just have to find enough different paths to arrive at that particular tensor structures. So in general, there's an infinite number of rate-shifting operators that you can construct. So you can always try to find different paths of raising spin of the seed solution. And
I think there is a basis. I think even the counting is not currently known, but there's certainly given, let's say, correlator, there's a basis of tensors which span the, and then you have its coefficient. The coefficient will be the scalar functions, and then you have a basis of tensors. Now, using the procedure you're describing, okay, you can find some solutions. The question is whether you can construct the complete basis rather than kind of a special subcase.
Yeah, so in our analysis, we used a finite number of operators as a seed basis for these rate-shifting operators, and those were enough to construct the desired correlation functions for this particular stress tensor correlation that we considered.
But how do you know you're not missing structures?
No, for the particular examples that we studied, we were not missing any structures, no. So we had like a basis of operators that we used now formalism, and you can basically take different ordering of these operators, because these operators generally do not commute, and yeah, so basically we were able to generate all the desired structure for this particular example that we studied.
Sorry, can I make a comment, Hayden? I think this was proven in embedding space, because these weight shifting operators also can be constructed, for CFTs in embedding space. And there the counting of structures and a number of weight shifting paths that you need to construct all these structures was proven. And so these weight shifting operators are just Fourier transforms of these complete class of weight shifting operators in embedding space.
Okay, so you're saying there is a claim with a general proof, okay?
Sorry?
I just want to try to get the claim.
I think there's a proof. There's a proof. I can point you to these papers by Simmons, Staffens, and friends, where I think they prove a lot of formal group theoretic results about these weight shifting operators.
No, Daniel, but I think Costas is asking something different, which is, well, maybe I'm misinterpreting the question. I thought the question is, can you build a basis of all tensor structures that satisfy the Ward identity kinematically, regardless of any dynamical inputs?
Yes, yes, exactly.
And this, I'm not sure, has been proven. In fact, even in flat space, classifying all possible contact interactions between multiple gravitons at 4 points, I think has only been done like very recently by Shiraz Minwala and collaborators. So we wouldn't even know what to match to, even after imposing dynamics. So at the level of kinematics, as far as I know, the state of the art is some counting by Tolia-Dzimarsky.
Yes, yeah, that's what I was saying.
Okay, no, I mean, that's what I thought. I just wanted to make sure. Okay,
yeah.
Thank you.
Okay, thanks.
Sorry, can I ask also something? So sometimes it can happen then when you do this kind of operations, you start with some correlation functions that's non-local, but you end up with something completely local. does it deal with this issue here? Or right, because you start with let's say correlation functions of dimension, what is it, 2 or 1 in the equals tree, right? And then as you go higher in dimension, you should start generating logarithms. But it's very likely that you will only find local solutions.
Yeah, it is true that sometimes when you act with these differential operators on logs and transcendental functions, you generally find that transcendentality goes down when you act with this differential operator. So yeah, in those cases, I think needs special care. And
perhaps we should postpone the remaining questions till the end of the talk, just so Hayden has enough time to finish. Thank you.
Actually, I'm going to focus on the second approach that we used, which is by exploiting the singularities of correlators to construct these spinning correlation functions. So as I described earlier, physical correlation functions are characterized by their behavior in the vicinity of their singularities. So for example, we need to have a total energy singularity at which the correlator reduces to the corresponding amplitude in flat space, and also has to factorize correctly on partial energy singularities into a product of lower point structures. And moreover, it shouldn't have any singularities in the collinear limit. So the advantage of this method compared to the previous one is that the building blocks are much simpler since we just need to know the 3-point functions, which are completely fixed by symmetries, and also the amplitude in flat space that has a known simple structure. So we find that demanding consistent behavior on all of the singularities is actually enough to uniquely fix the answer in many cases. Okay, so we'll now try to directly construct these spinning correlation functions, open functions, by exploiting their singularities. So this is quite similar in spirit to the 4-particle test for amplitudes that demands consistent factorization behavior at all singularities, but we also see that the details are slightly different. So before discussing correlators, let's quickly review what the consistency criteria are for amplitudes. So fundamental physical principles that control the structure of amplitudes are locality and unitarity. And because of locality, the only type of singularity that amplitudes can have at tree level are simple poles when the intermediate momentum, intermediate particle is potential. And unitarity then implies that on this pole, the 4-particle amplitude must factorize into product of on-shell 3-point amplitudes summed over all possible intermediate helicities. Although constructing consistent amplitudes works trivially for scalar particles, which can be done by simply adding different channels with the correct residues, this is no longer guaranteed to work for massless spinning particles. This is because 3-point spinning amplitudes are superficially non-local with high-order poles, so that a single factorization channel can have high-order poles, some of which can come from multiple channels, so, which makes it non-trivial to find an object that consistently factorizes in all different channels. And it turns out that this relatively simple constraint of consistent factorization is extremely powerful, which can not only be used to construct a full answer for the amplitude, but also strong enough to rule out inconsistent theories. It turns out that we have a factorization condition for cosmological correlators. And in particular, correlators of conserved currents at tree level are also rational functions with poles corresponding to the total energy and partial energy singularities. As I mentioned before, reaching this partial energy singularity is like enforcing energy conservation on one of the vertices. So at the singularity, so 4-point function factorizes into a product of 3-particle amplitude and a 3-point correlator. Here, more precisely, it is the so-called shifted wave function that appears on the right-hand side, which is found to be the difference between 2 wave functions with opposite signs of the intermediate momentum. And we find that this factorization constraint, when combined with other singularities, such as the total energy singularity and the absence of collinear singularities, provides a powerful constraint on the form of the correlation functions. Okay, so to quote Enrico, an example can worth 1,000 words. So to see how this procedure works for correlators, let's now go through a few examples. So let's start by looking at the simplest example of the 4-point correlator with 1 spin, 1 current, and 3 scalars. So in order to construct this object from factorization, first need to have the 3-point building blocks, which take this relatively simple form as shown here. Notice that these 3-point shifted wave functions, because obtaining them requires flipping one of the signs of the energies. They naively contain collinear singularities. So when constructing this correlator by gluing these 3-point structures, we will need to make sure to find an object that is free of these collinear singularities when going away from these factorization limits. Okay, so let's now take a look at what the consistent factorization limits are. So notice that because the correlator is asymmetric in their external legs, we get slightly different expressions for the left and right energy singularities here. Now the task is to find an object that factorizes correctly in both singular limits as shown here. So when comparing these two limits, we see that they look very similar modulo small differences. So one of the differences is the factors in the denominator, which are -2s on the top expression and k12 minus s in the bottom expression. So this apparent difference arises because on the left energy singularity, the top expression, k12 is precisely equal to -s on this singularity. So these factors in the denominator are really the same factors in disguise. Another apparent difference is inside the log, where we have k34 minus s for the left singularity on the top expression. Again, here, replacing s with minus k12, we find that this vector can be expressed as a total energy E away from the factorization limit. So combining all of these facts, we find that there's a unique object that factorizes correctly in both limits in the S channel with no superior singularities. So by demanding consistent factorization, we have constructed this correlator in the S channel. But before claiming victory, we must still check whether this object still satisfies the current conservation condition. Okay, so to check this, we take the explicit action of the conformal generator on this S channel correlation function. As we saw, this doesn't completely annihilate the correlation function, but spits out the longitudinal part when you activate the conformal generator in spinor variables. And that gives these particular terms on the right-hand side of this top expression, which has 3 different types of singularities. Now, the Ward-Takahashi identity asserts that the longitudinal part of this 4-point correlator should be given in terms of a sum over 3 scalar 3-point functions with appropriately shifted energies. However, we immediately see the tension between the 2 expressions because they have different types of singularities. So we see that the only way to rectify the tension is to add all of the 3 different channels so that we have all 3 types of partial energy singularities in green that match the ones coming from the Ward-Takahashi identity, and then demand that the charges further add up to 0 so that the log E and the 1 over E singularities in red cancel amongst the channels. And for this cancellation to occur, we need to have at least 2 different channels. So let's summarize what we've just done. So first, we've succeeded in constructing the correlator in the S channel by demanding consistent factorization. And then we found that for this to conform with the Ward-Takahashi identity, we must add multiple channels and further demand that the overall coupling constant add up to 0. So in the end, we have succeeded in constructing the full correlation function, and also we have rediscovered the bulk charge conservation in a purely boundary way. A similar story holds for the non-abelian Compton correlator with 2 spin 1 currents outside. So this example is slightly more non-trivial than the previous one, since we now have to also allow for the possibility of exchanging a spin 1 current as well as a contact diagram. But we essentially follow the same procedure. So first, we construct a general correlation function that correctly factorizes in all channels. Next, acting with the spatial conformal generator on this general solution, and then comparing with the right-hand side of the Ward-Takahashi identity, you'll find a mismatch between the types of singularity in the two expressions. So in this case, this can be fixed in two steps. So first, we must add the contact diagram to reproduce one of the singular terms in the Ward-Takahashi identity. And then we must demand that the coupling satisfy a specific anti-commutation relation for some of the singularities to cancel among themselves. So in this way, we rediscover the bulk fact about the coupling matrices obeying the Lie algebra structure of the Yang-Mills theory. Another example we can consider is the graviton-Compton correlator with two stress tensors and two scalars outside. So this is essentially equivalent to the previous example of the non-linear Compton case, but just with a slightly more involved algebra. So again, after constructing individual correlators for each channel from consistent factorization, the conformity with the Ward-Takahashi identity is only achieved once we also add a contact diagram. And in this case, we must set all coupling constants to be equal to each other, which is actually nothing other than the bulk equivalence principle. Okay, so we have combined factorization and current conservation to reproduce bulk facts about charge conservation and the equivalence principles from a purely boundary perspective. And we found that the current conservation condition can only be satisfied if all channels are added with correlated couplings, reflecting the fact that individual channels aren't really physically meaningful, but only their sum is. This is, of course, directly related to the on-shell Ward identity for amplitudes, which imposes gauge invariance of the full amplitude. So we can also derive the same bulk effect in a slightly more on-shell fashion without relying on checking the Ward-Takahashi identity, but rather just demanding consistent behaviors on all singularities. So this is closer in spirit to the usual on-shell four-particle test for amplitudes. So this time, not only demanding just a consistent factorization behavior at partial energy singularities, but we will also demand a consistent behavior at the total energy pole. Now, one thing that we can do is simply to match the residue at the total energy pole with the known amplitude in flat space. While that's also perfectly legitimate to do so, our goal is to rederive the bulk fact without really knowing the answer a priori. So rather than trying to match with the amplitude directly, we can also try to impose a slightly weaker but also necessary condition that the residue at the total energy pole must be Lorentz invariant. What we would like to do here is to take the simultaneous limit by sending E to 0, as well as the energies K1 and K3 to 0. A nice thing about this analysis is that because we're taking several limits, the algebra becomes quite simplified and can be done in just a few lines. When we take these limits, we find that the individual channels and the contact diagram has this following singular behaviors in a Lorentz violating way. So here, the capital ST and U are the flat space and Mandelstam variables. And adding up these contributions, we find that the only way to make these bad singularities to vanish is to set all the gravitation couplings to be equal to each other, hence reproducing the previous result. And once we fix the couplings this way, the fact that the correlator reduces to the amplitude on the total energy pole becomes an output. Okay, so as our final example, let me show you a cute no-go result we can derive from this on-shell consideration of the correlator. Let's consider the 4-point function of a massless spin L particle coupled to 3 scalars. And for simplicity, let's consider this correlator in flat space, which takes this rather simple form. Now, as before, we take a linear combination of correlators in all channels and take the total energy going to 0 and K1 going to 0 limits simultaneously. And this gives this particular expression in terms of the Mandelstam variables in the second line. And notice that this naively is singular for spin 1 and higher. So now we require that this singular piece must vanish when sending K1 to 0. So for spin 1, these Mandelstam variables are just become 0th powers. So this Lorentz violent singularity vanishes if we impose charge conservation. For spin 2, as a consequence of momentum conservation that S plus T plus U goes to 0, this vanishes if we set all the couplings to be the same, again leading to the equivalence principle. However, it's easy to see that it's also impossible to make the singularity vanish for spins higher than 2. And this is, of course, nothing other than a re-derivation of the Weinberg's soft theorem, now from an on-shell constraint of cosmological correlators. Okay, so to summarize, the take-home of our work is that it's possible to construct spinning correlation functions from simple building blocks, and then use consistency conditions to obtain the unique answer with correlated couplings. So before concluding my talk, let me spend just the last few minutes discussing some open problems. So although the method that I described allowed us to generate many new theoretical data for cosmological 4-point functions, we are still lacking some simple tools to compute more complicated examples like the pure graviton 4-point function. So we'd like to know whether there's a more efficient and systematic way of constructing these correlators. And because we precisely know the locations of all the physical singularities of tree-level spinning correlators, we might think that it's possible to derive these conformal spinning correlators by starting from a suitable ansatz. Because it's possible to check conformal symmetry and current conservation with a single equation, namely the spinor version of the Ward-Takahashi identity, we might think that it's possible to algebraically solve the on-shell constraints by writing down the most general polynomial that has the correct conformal and helicity rates divided by the expected singularities and just try to fix the coefficients. For example, a similar exercise for amplitudes were carried out in these references on the bottom, finding that indeed the assumption of singularities together with gauge invariance was powerful enough to fix many amplitudes. For correlators, it turns out that this can indeed be done for 3-point functions, and once one is able to write down a closed form expression for Massless 3-point function with arbitrary spins. The problem for a 4-point function is actually much harder, it turns out, because not only there are many more singularities and coefficients to solve, there are also multiple allowed spinor structures. So currently we are trying to understand what the most convenient basis of spinor brackets to use this for this purpose. But we think that the problem should be eventually solvable with some advanced computer algebra. Another interesting question is to find the boundary equation that governs the structure of correlators and encode bulk time evolution in cases where there is no conformal symmetry. For example, it would be particularly interesting to find an equation for flat space correlation functions, which are much simpler than their de Sitter counterparts. This would be quite useful since correlators in flat space and de Sitter are typically related by some integral differential equations, so that the de Sitter correlators can be straightforwardly obtained from the knowledge of flat space correlators. Some relations of this kind have been derived, including equations for the scalar 4-point functions and the one that has one Massless spinning particle as shown here. So this is closely related to looking at the integrand of the wave function like Paolo and Nima have studied in their papers. So it would be very interesting to see if this uplifting procedure from flat space to de Sitter can be systematically generalized to spinning correlators. Okay, so in my final slides, let me just very quickly mention some other interesting open problems. So first of all, there are several questions that can be naturally explored by further extending our current formalism on spinning correlation functions. So for example, the next transition in our understanding of spinning correlators would likely occur through the discovery of the Park-Taylor correlator, that is obtaining the general form of pure gluon correlation functions. So in flat space, the celebrated Park-Taylor formula for gluon scattering amplitudes has an extremely complex structure. So we might expect a similar simplicity in the final answer for these gluon correlators. Also in flat space, on-shell recursion relations such as the BCFW recursion has now become a standard technique for calculating scattering amplitudes. So we'd like to see if we can derive a similar relation for massless spinning correlators. So far, we've only used a consistency condition for correlators to reproduce the uniqueness of known theories in flat space, namely Yang-Mills and Einstein gravity. But we would like to see if we can constrain or rule out interesting theories that do not necessarily have counterparts in flat space, like theories of partially massless field in de Sitter. In general, analyzing conformal symmetry is typically harder in momentum space than in position space because we don't quite have conformally invariant building blocks in momentum space. So it would be nice if you can find and utilize more natural momentum space building blocks that trivialize special conformal symmetries. And so far in our work, we have focused our attention exclusively on tree-level correlators, but the study of correlators at loop level will be an important next step. We would like to also understand what the implications of bulk unitarity are. And an interesting result was discussed in Harry and Enrico's talks. So it would be nice to know what the full consequence of this is combined with the ones that I discussed in my talk. Also, while our philosophy has been to bootstrap correlators from a purely boundary perspective as much as possible, it can also be very useful to consider the Mellin or frequency representation of the bulk correlation functions. So it would be interesting to explore this further and try to make a sharper connection to the known result in ADS. And finally, we can wonder whether there exists any autonomous geometric or combinatoric structure that gives rise to these correlation functions, similar to what has been found for scattering amplitudes. So hopefully, Paolo will tell us more about this very soon. Okay, so hopefully you've been convinced that the boundary formalism offers a very interesting perspective to study the physics of cosmological correlation functions. And that's all I have to say. Thank you for listening.
Thanks very much, Hayden. Does anyone have any quick questions?
I have a very quick question. Hayden, you mentioned about these transforms from flat space correlators to de Sitter correlators. Those are one channel at a time, right? Or
That's
not?
right.
Is there? Okay. So you don't have a picture for what would take a full sum over channels correlator in flat space and turn it into the analog in de Sitter.
Yeah, that's a great point. Yeah, so that's definitely something that we have in mind ultimately deriving. Right now, the relation that we have found is working for channel by channel.
Channel by channel. Okay, thank you.
I have a question about this four-particle test in de Sitter. So in particular, when you do it for amplitude, the interesting thing is to see that there are, when they are available, some higher derivative interactions that various spinning particles can have. While it seems that what you presented are just the one that you already knew are the lowest derivative possible interactions and are the minimal ones. But did you look to see if there are some consistent higher derivative ones, as well as, do you have a more generic statement about possible interaction of higher spin particles in de Sitter, not on the amplitude?
Yeah, so yeah, that's along the lines of what we eventually want to look at. So we want to basically apply this full particle test to more general types of interactions, especially involving those involving higher spin interactions. So I think, yeah, this particular result that we derive somehow doesn't rely on the existing flat space result. So of course, I think we can also go to the total energy pool and then just simply run through the flat space argument by demanding consistent factorization behavior, and we will arrive at the same result. But here, I think we slightly impose a weaker condition precisely because we don't want to rely on the flat space result by demanding that this particular Lorentz violin pole should be absent of the total energy pole. I'm not sure how this type of constraint would generalize for more general types of higher spin interactions in de Sitter, but I think it will be yeah, something that we definitely want to look at.
So I didn't understand this slide because maybe I think I misunderstood because it seems trivial to me. It seems you're taking the total energy pole and then it's just the amplitude, and then you're proving Weinberg-Soft theorem on the amplitude, which was proven 60 years ago. But is something different?
I think this is slightly different. So we are slightly imposing a weaker condition. So we are not demanding that the residue at the total energy pole matches with the amplitude, but rather that becomes an output in this procedure. Because here we are taking one further limit by sending K1 to going to zero limit. And we are demanding that this particular singularity behavior, as we take K1 to zero, vanishes on this total energy pole. So I think that's a slightly different and weaker condition that we are imposing.
I have one comment and a question, if I can ask. One comment also about Nico's question is that actually, we have a work in progress with Charlotte, which was presented also at some various conferences, in which we are able to do some constraints on spinning particles, including partially massless particles. And the question, which is related to actually Hayden's talk, is that you focus on conformally coupled scalars, right? Correlators with conformally coupled scalars. But the equivalence principle is something that should not really be about conformally coupled scalars. So my question is, can you really extend your logic in an easy way to arbitrary massive scalar at least? Or do you have any comment about this?
Yeah, so I think these examples that we studied are always mixed correlation function between stress tensor and conformally coupled scalars. But I don't think this analysis will depend on the type of scalar field.
Yeah, but how do you see? How do you expect it to? I mean, there should be a proof that of this that is completely doesn't rely on any simplification associated to the conformally coupled scale.
Yeah, I think. Yeah, we didn't do the some explicit computation other than conformally coupled field. But my general expectation is that, for example, you can try to run through the same logic for couplings to massless scalars outside.
The massless scalars we did, Hayden, in the paper.
Because that you can obtain
for this graviton component, yeah.
Yeah, it's not just applying weight shifting operators, because you need to change the mass of the internal guy also to be compatible with the equivalence principle, but yeah, you can also do it for massless. And at 3 points, I think we did it for a generic mass, just that the 3-point function between graviton and two scalars requires that both scalars have the same mass, but not what you would like, the Compton case for arbitrary mass, which is interesting, I think. It's just that the singularity structure becomes more complicated in that case, right? So it's harder to bootstrap.
Sorry, guys. I mean, if one wants the kind of one-line reason why it has to be, you just need the argument that that on the K-total pole, conformal invariance implies Lorentz invariance, and then you're done. Then you just go back to the amplitude argument. So the entire subtlety, I think, is showing that you actually get Lorentz invariance on the K-total pole, even though it naively is. But it's what you would expect without thinking, because the special conformal operators become boost operators on the K-total pole. Then there's some a little bit of subtlety, but that's the fast reason why it has to be true.
Yeah, I would like to emphasize the subtlety in that reasoning. Maybe you can convince me that it's not a loophole, but. So there are a few caveats to the general statement that the amplitude is the residue on the total energy pole. And I think I would like to make several, but one of them is that there are cases in which the amplitude is 0. Then it's still true that it is the residue of the total energy pole, but that 0 divided by the pole. And so you move on to the subleading one. So one loophole could be that although the amplitude is forbidden, the amplitude is 0 in flat space, there are some subleading terms in KT that do appear when we look at the cosmological correlator.
Sure, like the all plus gluon correlator. Yeah, is exactly an example like that. Right. Yeah. No, but I just meant for these for the discussion of equivalence principle, consistent theories, etc. I'm just saying the obvious thing that when the amplitudes exist, we can get them by going to the K-total singularity, and then the only argument needed to connect them is that conformal invariance turns into Lorentz invariance. I mean, because we're assuming Lorentz invariance on the flat space amplitude, so we have to know where that comes from, and that comes from conformal invariance on the K-total singularity.
Yeah, I agree with that.
But there are extra subtleties. I mean, that just shows that things that are inconsistent in flat space will be inconsistent in de Sitter. However, there are things that are consistent in flat space that are inconsistent in de Sitter, like gravitinos. So that's extremely interesting to try to understand. I mean, I think we know how it should work, but anyway, you know, there are things that are inconsistent in, and conversely, maybe there are things that are only consistent in de Sitter. I know, I mean, obviously, partially massless is an example of something you can't even talk about in flat space. But I don't know if there are any examples of, there are these funny interactions that are ruled out in flat space. There are these funny 3-point functions that are ruled out in flat space, where the sum of the helicities of the 3 particles is equal to 0. The only case which is consistent is the pure scalar case for that guy in flat space. But anything else, but they're illegal. I don't know if there are any interesting correlators. I doubt it, but anyway, there are some interesting cases of things that are inconsistent in flat space that it would be good to see if there's some way that they are consistent, maybe with interactions that are proportional to Hubble in de Sitter.
Yeah, I have some interesting example of those. For example, in flat space, you cannot, for amplitudes, you cannot couple a phi dot cube theory for a scalar consistently to gravity. There is no possible 4-particle amplitude that factorizes consistently if the scalar interaction is phi dot cube, namely if it violates Lorentz, and then it's coupled to gravity in any way you want. It's just impossible. While that coupling is absolutely present, and in fact is vital to many models of inflation when you move to de Sitter, more generally, any Lorentz breaking in Minkowski in amplitude cannot be coupled consistent to gravity, something that we showed earlier on this year, because just the 4-particle test fails. However, spontaneous breaking of boosts clearly does happen in cosmology, and in fact, that's what happens during inflation, where the inflaton selects a frame and can be, and in fact is consistently coupled to gravity. So I think those are an interesting class of cases that if you were to take the flat space limit, all those coupling should die away, because they are not allowed in, strictly speaking, Minkowski when Hubble is literally 0.
Perhaps in view of the schedule, should we take a quick 5-minute break and then resume to continue the discussion session?
Hi, can I ask you a quick question?
Sure.
So hi, Hayden. I'm wondering if I get you correctly. So the no-go example that you mentioned is a manifestation of the Weinberg's adiabatic theorem. So as violation, can I consider that as a smoking gun against the single scalar vacuum inflation?
So you want to
yes, so it's about your no-go example. Oh yeah, so if I understood you correctly, it's simply, so the logic is basically like the Weinberg's adiabatic theorem, right? So that one is for the power spectrum, but this is for endpoint functions.
Yeah, so this is similar to the Weinberg's soft theorem. You can prove using amplitude argument that yeah, you cannot couple matter consistent with massive size spin particles in flat space. Yeah, I'm not sure if I correctly understood your question.
Oh, sorry, it's only on the flat space. It's not about the cosmological background. Oh.
Yeah, so this particular example that we looked at is the flat space correlation function. So this expression that I'm showing you is the correlation function in flat space, actually.
Oh, I see. But then the rest of the argument, if instead of one single scalar vacuum inflation, I have other stuff like a vacuum of gauge fields or other fields, would that violate anything? Oh, I guess maybe it's not a short question. Maybe
maybe we can.
Would this connect with cosmology with high spin gauge fields?
Like yes, actually, because there is a class of inflationary models based on having non-abelian gauge fields with a VAV, and that actually leads to a new mechanism for generating gravitational waves, and it's testable by future CMB missions like LightBird and CMBS-4.
Like with the same logic, that would be one high-spin gauge field and then 3 scalars in the bulk and the sitter.
Actually, no, it's not the same, because the non-abelian gauge field has a
no-go theorem on the slide. So it seems to me the no-go theorem in the slide also applies to the sitter with high-spin gauge fields.
I don't think so. At least my understanding of the Weinberg theorem is based on, so the cosmological version is when the anisotropic tensor goes to 0, when k goes to 0, while in the presence of the gauge field, it's softly broken. So after horizon crossing, we also leave with some sort of anisotropic tensor. So in a way, that softly broke the Weinberg's adiabatic theorem.
I think here we are discussing two different Weinberg's theorem. One is from 60 years ago, and it's about soft limit of amplitude, and one is from 2005, and it's about the existence of solutions that are continuously connected to large diffeomorphisms in a Ferrer W space-times, which is the adiabatic modes that you're talking about, Azadeh.
Yes. Yeah, thanks, Enrico.
I think maybe Hayden here had in mind the soft limits for amplitudes.
I see. Thanks.